Today we're going to do the notes for 3.3 about plate tectonics and the landforms that they create. So if you can think back to 3.1, we learned about what is plate tectonics, how did we get the theory that we have today? Remember that whole thing about Alfred Wegener with continental drift and then us realizing he wasn't so crazy. And then 3.2 is about the different types of boundaries. So we have convergent where they come together, divergent where they move apart, and transform where they scrape past each other. And then 3.3 is going to be about when those plates move and when they interact with each other, what kinds of landforms do we get? So the theory of plate tectonics just explains how those rocky lithospheric plates move around on top of that toothpastey tar-like asthenosphere. This diagram that we have here on this slide is a screenshot from your book. This shows a convergent boundary between an oceanic plate and a continental plate. And you see that oceanic plate is sinking or subducting underneath that continental plate. When this happens, you're going to see two different landforms. We see a trench here, right here. That's happening because that oceanic plate's kind of dragging that continental plate down with it as it's sinking. And then our continental plate is also going to have some mountains and volcanoes that happen on it, partially because it's kind of crumbling up, but also partially because some of that stuff from that oceanic plate is starting to interact with the mantle, causing some bubbling up of that mantle material. So something that's important to remember about tectonic plates is not every plate is the same. Okay, we have tons of different tectonic plates all around the world that are different sizes. Some are very tiny, like the little Nazca plate that's over in the Pacific Ocean. Some are a lot bigger, like the North American plate. So they're different sizes, different shapes. It's kind of like if you were to crack an egg, how it doesn't crack all in the same shape. But the most important property of a tectonic plate is its density. Different plates and different types of crust have different densities. Oceanic plates in general are much denser because they're squished down. They're much denser and they're much colder than continental plates. Continental plates are thicker and they can be up to, according to this diagram here, it says 70 kilometers thick. Whereas ocean plates can be 5 to 10 kilometers thick. So it's much, much more squished down. Sometimes plates have both types of crust on them. Like you'll see oceanic crust on one side and continental crust on the other. So sometimes you'll see both types of crust, but where we see that oceanic crust, we're going to see it being a lot thinner, a lot denser. Continental crust is going to be a lot thicker. Continental crust in general is a lot older. And oceanic crust is a lot younger because we see new crust getting created most often in the oceans. So when these plates come together, they cause what we call stress. Okay? Different types of stress are related to the different movements of these tectonic plates. So when plates are stressed, that causes some what we call deformation in the plates. That deformation can be either some folding, it can be some stretching, it can be some bending or twisting of the rock. But when we see those plates move and change direction and things like that, you're going to see deformation happening. There's three main types of stress. First is compression, and that's what we see here in diagram A. This is another screenshot from your book. This is an example of compression. Compression happens when two plates come together and they get squeezed. Okay, you know what it means for something to be compressed. That means like pressed together. That is an example that happens at a convergent boundary where plates are coming together. Stretching or tension stress happens when plates pull apart, so at a divergent boundary, so when they're moving away from each other. That causes tension. This will often cause some faults, so breaks in the rock, so you'll see uneven rocks as they get kind of pulled apart. Shear stress which we see here in diagram C. Shear stress happens as rocks kind of move unevenly as they sort of like move past each other. So you'll see those rocks getting twisted, bent, distorted. This is going to cause a lot of earthquakes and faults. So we have a couple of different types of plate boundaries that we'll see here. I'm going to move my video up there. We have a couple of different types of plate boundaries. The first one is your convergent boundary, where those plates are coming together. There's 3 different kinds of convergent boundaries, and I think convergent is probably the most complex of all 3 types of boundaries. Convergent boundaries can happen between an ocean plate and a continental plate. That's what we see here in this top diagram. That ocean plate is very thin, it's very dense, and it's very cold. So it's going to subduct underneath that thicker, fluffier, if you will, continental boundary. So subduction, remember, is a term for when a plate sinks underneath another one. So that thinner oceanic crust is going to subduct underneath that less dense continental crust. So when they come together, that thinner oceanic crust will subduct underneath that thicker continental crust. This is going to cause, like I said a couple slides ago, a trench here and maybe some volcanoes. Definitely some mountains. That's where we see coastal volcanoes like the Andes Mountains, the Cascade Mountains, where in Washington, like the Pacific Northwest, those are all happening because of an oceanic plate and a continental plate converging. The next kind of convergent boundary is if we have 2 continental plates coming together. 2 continental plates are going to have the same density. You're not going to have one that's more dense than the other. So instead of one sinking underneath the other one too much, what you're going to see is more of a crumbling upward. This is how the Himalayas are forming. And I say forming because they're still growing taller every year. So the Himalayan mountains, where Mount Everest is, at the top or the northern part of India, the Himalayan mountains are happening because there's a continental plate in India and a continental plate in Asia that are meeting and coming together, and they're just folding and getting taller and taller and taller every single year. So instead of one sinking underneath the other one, they're going to crumble and push upward. The third type of convergent boundary, is where we have 2 ocean plates coming together. Now, I know I just said that all continental plates are the same density, but that's not true for ocean plates. Some ocean plates are a little thinner and denser than others. So the thinner, denser oceanic plate will sink underneath the thicker, slightly less dense oceanic plate. This usually happens because that denser oceanic plate is a little bit older, so it's had more time to cool down. And when things are cooler, then they become a little bit denser, usually. But also because it's had more time for that ocean to squish it down, to make it really squished down and dense, okay? So the older, colder, denser plate will subduct underneath the other oceanic plate. When this happens, we're going to see another trench where that subduction is going to kind of pull that material downward, but you'll also see some volcanic islands. Again, we'll see these volcanic islands because we've got a lot of stuff on the ocean floor that's getting dragged down into the mantle, a lot of carbon, which is like, dead plant and animal matter. And all that stuff and all that water that's getting pulled down there is going to react with the mantle, causing some crazy melting things to happen and causing some magma to come up through the crust. So you'll see volcanoes on top here. This is going to look more like islands, whereas the volcanoes on top of the subduction zone with the ocean continent convergent boundary is going to look more like mountains on the coast. These volcanic islands, a good example of these are like the Aleutian Islands. So the little tail at the end of Alaska. So if you're picturing a map of North America, you know how we have Alaska that's kind of hanging off the side of Canada, and Alaska has this little tail that's going. And all those little islands that are making up that tail, a lot of those are volcanic, and a lot of them were formed from volcanoes because of an ocean-ocean convergent boundary. Divergent boundaries happen when crust moves apart. So when crust moves away from itself, it's going to create what we call a rift valley. So we see that animated right here, up here in the top. Well, it's not animated, but drawn up here in the top. So crust is moving away from itself. We see this gap being a rift valley. Sometimes that rift valley might fill up with water eventually, and then it might get so thin that it can create room for magma to come up and through, so new ocean material and new crust material to come up through. A lot of these divergent boundaries happen in the ocean. Most divergent boundaries happen in the ocean. A perfect example of this is the Mid-Atlantic Ridge. The Mid-Atlantic Ridge is running right down the center of the Atlantic Ocean, and it is literally ripping apart anything that sits on top of it, including a very cool island called Iceland. Iceland is getting torn in two between the North American plate and the Eurasian plate. That island sits on that plate boundary. So you can stand on the North American plate and then travel over to the Eurasian plate, and you can be on two completely different tectonic plates in the same day. A lot of people can go like snorkeling and stuff in between those tectonic plates. Up there, it's like a big tourist attraction. It's pretty cool. Deeper in the Atlantic Ocean, once you go like farther down, the Mid-Atlantic Ridge basically looks like an underwater mountain range because it's those two plates that are pulling apart from each other. And when they pull apart from each other, that's leaving room for magma to come up and out of that area, of that rift valley. When magma comes up and out, but it's in the ocean, then it's going to cool down super, super fast. When magma cools down, it becomes hard rock. So basically it's going to harden really, really soon after it comes out of the ocean floor. Not like a volcano that you might see on Earth where you see like time for all of that magma to drip down. You know, if you've ever seen like Hawaiian volcanoes where it's like oozing, goozing. There is not a lot of time for that in the Atlantic Ocean or in any ocean, because it cools down so fast, it hardens and becomes these underwater mountain ranges. And these underwater mountain ranges kind of circle the globe, sort of like stitches on a baseball. It's very cool. The third type of boundary that we're going to talk about is, I think, the simplest type of boundary. It's the transform boundary. Transform boundaries happen when plates are just sliding past each other. This is going to give us some faults and some earthquakes, but it's not going to cause like major mountains or valleys or trenches or things like that. You're just going to see those plates that are scraping past each other. A perfect example of a fault that we should be familiar with is the San Andreas Fault, which is out in California. So part of California is literally moving northward while the other part of California is moving southward. And you can see there's like a map here. This red line is the San Andreas Fault. You can actually walk up to the fault and see how the two plates are kind of offset from each other. This picture here is kind of cool because you can see this is a dried up riverbed that was sort of offset from itself. This is a video from BrainPop that is just going to go over all the different tectonic plates.
Enjoy this movie, then visit brainpop.com for much more. Are you sure this thing is rated for this depth? You bought it from an Air Mall catalog. Oh, great. Dear Tim and Moby, when I look at a map, it seems like some continents fit together perfectly. Are my eyes playing tricks on me? From Georgia. You're not seeing things, Georgia. Some continents look exactly like puzzle pieces that snap together. Early map makers suspected that they were once all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangaea. He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continents we know today. Wegener couldn't explain why Pangaea split up or how. But there was some evidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers matched up too. Wegener's theory of continental drift provided an explanation, but his ideas weren't taken seriously until long after he died. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that the farther you got from the ridge, the older the seafloor was. So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading. It seemed to indicate that rock was being forced up from inside the planet.
This is at a divergent
Nowadays,
boundary.
we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at the time. As he suspected, there's a lot going on beneath the Earth's surface. Up here, everything seems pretty cool and stable. But miles below our feet, it's a raging inferno. The deeper you go, the hotter it gets. Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape, like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section, the mantle. Standing in its way is the lithosphere, a rigid layer of solid rock. Well, the lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates. Yep, the Mid-Atlantic Ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics. It's the engine driving the constant transformation of our planet's surface. Plates have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding around under our feet, but we do sometimes feel it. Yep, I'm talking about earthquakes. Seismic activity is greatest along plate borders. At convergent boundaries where two plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other. At all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Yep, and plate movement drives volcanic activity too. At divergent boundaries like the Mid-Atlantic Ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland. The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust. It also creates our most prominent geologic features, mountain ranges. That happens when two continental plates converge. Since they're both about the same density, neither one subducts. Instead, it's like a slow-motion car crash. The plates buckle and warp. The land pushes up into jagged peaks. The Himalayas are still growing from a plate collision that began 500 million years ago. Yeah, Alfred Wegener's theory has come a long way in 100 years. He was practically laughed out of the scientific community for his ideas. But today, plate tectonics is the unifying theory that ties together the entire field of geology. What do you mean, out of juice? We're stuck here? Now what? Oh, thank you. Visit us at brainpop.com for more on this topic and hundreds of others.
Okay. So we just learned about like what happens at each one of those boundaries, where we have convergent boundaries where those plates are coming towards each other, divergent boundaries where they're moving away, and then transform boundaries where they are moving past each other. Here, we're just going to go back over the specific landforms that we see. I already mentioned many of them, but this is just the notes that get a little bit more specific about it. So at convergent boundaries where plates are moving towards each other, you're going to see a couple of different kinds of mountains. First are folded mountains. This is like the Himalayas that they were just describing in that Brain Pop video about where they're talking about the two continental plates coming together. They're the same density, so they just kind of fold up, fold up, fold up. So you'll see those mountains growing taller and taller every single year. The Swiss Alps are another good example of this, although those ones are a little bit older. But the Himalayas are still growing today. Fault block mountains are another kind of mountain that happens. Instead of folding, we see more of a fracture of rock, and rock gets like shoved upward when those two plates come together. But it's still a convergent boundary where those two continental plates are moving towards each other. You're still going to see big mountain ranges. Just the difference is in a fault block mountain, you'll see an actual fault, meaning like a break in the rock, where rock is getting like physically shoved upward, whereas folded mountains, it's more of a slow building. We also oftentimes see volcanoes, like I was showing you a couple of slides ago. And when you see here on these slides, this O-C, the O means oceanic or ocean plates, and C means continental plate. So we'll see either a continental volcanic arc or what we call coastal mountains more often. Good examples of this, like I said, are the Cascade Mountains, like Mount St. Helens in Washington, the Andes Mountains in South America. Those are all good examples of these coastal mountains. But this happens when we have an ocean plate converging with a continental plate. Okay, so ocean plate and a continental plate. That ocean plate is going to sink underneath that continental plate or subduct. And as it's doing that, it's going to cause a major reaction as it's kind of going back into the asthenosphere. It's getting heated back up. It's starting to create a lot more reaction with the heat of the earth. And all of that stuff is going to bubble upward, causing those volcanoes to happen. We also might see volcanoes in the middle of the ocean. These are called volcanic island arcs. They're formed the exact same way. It's happening because of subduction, so because of one plate sinking underneath another one. Just the difference is instead of it being an ocean plate and a continental plate, in this case, we'll have an ocean plate and another ocean plate. But remember, the older, colder, denser plate is going to subduct underneath this slightly younger plate here. But same situation, as that plate is subducting, you're going to see a lot more of a reaction with the heat of the earth that's going to cause all that mantle material to bubble upward, bubble upward and cause volcanic islands. Good examples of these would be like the Philippines and Japan. They're formed this way. The Aleutian Islands, the ones that I said were like coming off the tail of Alaska, those are all formed in an ocean-ocean convergent boundary. All of those examples, so the Cascade Mountains, the Andes Mountains, the Philippines, Japan, the Aleutian Islands, every single one of those examples is part of that ring of fire that they were just talking about in that Brain Pop video. The ring of fire is kind of more shaped like a horseshoe than a ring, but it's more than a song. It is an area all around the Pacific Ocean where we see lots and lots of volcanoes. That's what gives it its name. It's because volcanoes are very fiery and hot. But what I want you to remember about the Ring of Fire is that it's not just volcanoes. It's volcanoes and earthquakes and faults. And I mean, it's all kinds of tectonic activity, trenches. So it's not just volcanoes. Even though I know we call it the Ring of Fire, we don't call it the Ring of Tectonic Activity because it's not as catchy. It's not just volcanoes. There's earthquakes, trenches, all kinds of other stuff too. A lot of fault lines. The next thing we'll see at a convergent boundary is a trench. Just like I showed you on that last slide here, when we have subduction happening, you see a trench where like one plate is kind of pulling the other one underneath. The best example that we have here on Earth is the deepest part of the Pacific Ocean, which is called the Mariana Trench. The Mariana Trench is kind of off the coast of the Philippines, and it happens because there's subduction happening. So one plate, the Pacific plate, is sinking, subducting underneath the Philippine plate. And it's kind of pulling it downward just a little bit with it, causing, this is actually a volcanic island here. It's not showing the volcanism here, but it's a volcanic island, but it's also causing this deeper part of the ocean, which is called a trench. The Mariana Trench, like I said, is the deepest part of the Pacific Ocean. There's some really cool, crazy things that live there. If you haven't done any kind of research into it, I highly suggest just do a quick Google search of what lives in the Mariana Trench, and you'll see some crazy things. Divergent boundaries, remember, these are the ones where plates are moving away from each other, so they're diverging. One of the things that we can see at a divergent boundary are some mountains. But instead of these being the fault block mountains where rock gets pushed upward, this happens because rock is actually falling downward, leaving behind a mountain. So one block of rock falls down against another one, or falls down next to another fault or another block of rock. A great example of these are the Grand Teton Mountains out west in the United States. Grand Teton Mountains are kind of cool because you see them, they're formed like a big mountain and then some flat land, and then another big mountain and then some flat land, and then another big mountain. So that is a telltale sign of some fault block mountains. Again, these are happening because these rocks are moving away from each other. So when they move away, they have nowhere to go but down because of gravity. Another thing that we see at a divergent boundary is rift valleys or rifts. This happens because that crust is getting pulled apart from each other, and that's just leaving a big open gap. Sometimes we'll see rift valleys on land. Like here we have the East African Rift up at the top of our slide here. So the East African Rift is very, very cool. This is where like Lion King takes place. So the East African Rift is where we see lots and lots of different types of wildlife and landforms and things like that. Mid-Atlantic Ridge has a rift valley running through it because it is getting pulled apart. This picture down here in the bottom right is a picture of, I believe this is taken in the Iceland area between the North American plate and the Eurasian plate, where they're kind of getting pulled apart here. Oftentimes you're going to see volcanic activity in the middle, but if it's not currently active, then people might go even like snorkeling in between those two plates. The Mid-Atlantic Ridge runs right down here, if you can see where my mouse is, through the middle of the Atlantic Ocean. But you can see we have these same kind of looking like underwater mountain ranges running all over the Earth. This is because the Mid-Atlantic Ridge is not the only example of a divergent boundary that's in the ocean. We have lots and lots of them that kind of circle the Earth like stitches on a baseball. Transform boundaries give us fault lines. We already talked about this one, but this is the San Andreas Fault in California. This part here, this is the Pacific Plate. It's moving kind of northwest, while the North American Plate is moving kind of southeast. So eventually what they say is the prediction is that like Los Angeles will end up so far north, it'll be like next to San Francisco, which right now it's like a 6 or 7 or 8 hour drive from San Francisco to Los Angeles. So the San Andreas Fault is our best example here. Typically, we see lots and lots of earthquakes, and those earthquakes happen because stress builds and builds and builds as those plates are trying to move past each other until all of a sudden those plates shift at one time. So all of a sudden those plates shift, and that's that release of energy that's going to give us earthquakes. We're going to cover earthquakes more in depth in 3.4. So we don't need to go into the physics of an earthquake quite yet, but that is the typical thing that we see happening at transform boundaries. The last thing I want to talk about doesn't happen at a plate boundary at all. This is a hotspot. Hotspots are super cool and they're super important, but they are nowhere near a plate boundary. They're not a convergent, not a divergent, not a transform boundary feature. They happen in the middle of a plate. Hotspots form because there's an area of the mantle that's just extra hot. Fancy that, it's called a hotspot. So it's a part of the mantle that's extra hot that wants to melt the crust on top of it. Typically, these hot spots form in the ocean because that ocean plate is a lot thinner. So it's easier for the hot spot to melt through that crust. So take a look at our diagram here. I'll move my video. So we have a hot spot here that is melting through the crust on top. When it melts through the crust, it's going to bubble through, it's going to release magma, it's going to build and build and build an island eventually. After a long, long time, that island is going to break through the surface of the water, and you'll see, land that's poking through the ocean. Well, we know that over time, plates move and shift and they don't stay in the same spot, but that hot spot, that hot part of the mantle is going to stay where it started. So the hot spot is going to stay where it started, but the plate on top of it is going to move. So this island that was created here in diagram 1 has now moved with that plate over. The hot spot is still there. So the hot spot is still melting the crust. It's still creating more magma. It's still building new islands. So now that the plate has moved, now we've got an open spot for this hot spot to create a new island. Over time, we're going to see that that plate is going to keep moving and changing direction over time. And so those two islands that were created before are now somewhere else. They have like drifted over to the side, or what Wegener would think is drifting, but we know they're attached to that plate and they've moved over. And our hotspot will create a new island. So hotspots can create island chains. This is how Hawaii, so our 50th state, Hawaii, this is how Hawaii was created, out in the middle of the Pacific Ocean. It's nowhere near a plate boundary. There's no convergent or divergent or transform boundary anywhere near Hawaii, but it's created on a hotspot. So the big island of Hawaii is still currently volcanic, whereas the farther away you get from that big island of Hawaii, the older the islands are and the less active they are, meaning like the less volcanic activity you see. because the hotspot is sitting here underneath the big main island of Hawaii. So this is the youngest, newest island. It's still it's still erupting today. So it's still building up. It's still getting built up today with new land erupting and stuff. But as that plate has moved, we can see the islands going with it. Typically, the islands that are farther away are a lot smaller. The reason for that is the ocean has eroded a lot of that land away. So it's possible that at one time, these tiny little islands that are here at the tail end of Hawaii, it's possible that at one time they were as big as the main island of Hawaii. I don't know for sure, but we also see evidence of older islands that have washed away underneath the ocean from the power of the ocean eroding the land. Hotspots are really cool because they help us track the exact direction and speed of the plate motion. So we can calculate how old these rocks are that make up these islands, and we can see exactly the direction that those plates have been moving. We can track this nowadays with our technology through like satellites, but old map makers used to be able to do this as well. This is a
Not all volcanoes form at plate boundaries. Some form instead in the interior of a plate, where geologists call them hotspot volcanoes or simply hotspots. One explanation of such activity is the presence of a mantle plume, a regionally restricted column of hot rock rising inside the asthenosphere. When it reaches the base of the lithosphere, the rock partially melts, sending intrusions of magma upwards into the plate. Some of this magma erupts to form active underwater volcanoes, or, if activity is sustained, an active volcanic island. An entire chain of such islands forms because the plate carrying the volcanoes moves across the stationary hotspot inside the asthenosphere. This movement slowly carries the active volcano off the mantle plume, causing it to go extinct. A new island grows in its place over the plume.
So we can use these hotspots to track the direction of this plate movement. Right now, we know that this plate is moving, I guess, westward. But if that plate were to switch direction, which it will in a minute, we can see that
when the plate motion changes, so does the direction of the volcanic island chain.
The hotspot helps us track that, to see where new islands are created.
The inactive older islands cool and subside with distance to the heat source and experience significant erosion. With time, former hotspot islands turn into smaller, shallow islands and ultimately become underwater seamounts.
And Hawaii has a lot of those off its tail end. We have a lot of those underwater seamounts.
Through geological time, the direction of the plate motion is recorded by this hotspot track of islands and underwater seamounts.
So that is the end of the 3.3 notes. That was a very long section. Send me an email if you have any questions, and I will be happy to answer them for you. Your book is a great resource for asking questions and, figuring out, looking at those diagrams. Also, the YouTube videos, the two of them that were in this set of notes, the two YouTube videos that I embedded into your notes should be helpful.